So I would like to present Antonio Krüger, who is not only a full professor at Saarland University, but he's also the Chief Scientific Officer and CEO of DFKI, which is the German Research Center. And I have the pleasure of working with a number of his colleagues at DFKI. And I've also heard you talk, and I think it's really important to get people who are really working on the edge between human-computer interaction and AI, but who also have a foot not only in research, but also looking at industry. So thank you, Antonio.
Wendy, thank you very much. I'm very much looking forward. I already enjoyed actually the first presentation from Wendy, which is, and I'm really looking forward to the discussions we will have. And I would like to provide an input, that is trying to explain, or basically tries to address this these two different fields and the gap actually between HCI and AI. And if you think about this, and I think Wendy made a good case here, is actually that with the advent actually of more and more intelligent systems, whatever intelligent exactly means, but I think we have a rough idea what it means, because it's a definitely a shifting goal in a way. Actually, the research is also changing in HCI. And if you look at HCI research, there is this kind of original tradition where it comes from ergonomics, where you really address the problem of interaction as a real kind of a problem, how to improve the tool. And now we have all the tool is still there, but we have all these different variations. I think Wendy explained actually this also paradigm shift in the research very well. First of all, I would like to thank my students that with whom I work together, and who have contributed also to the research that I will present it to you. But those are actually PhD students of mine, but I'm also presenting to you work from colleagues from DFKI. Wendy mentioned this, I have fantastic colleagues. DFKI is a 30-plus-year-old institution with, at the moment, 24 research groups, with fantastic colleagues, and they do all kind of different interesting things in the realm of AI, but DFKI always has been a very applied institute, so we're working a lot of industry. 2/3 of our projects are with industrial partners. They're not all industrial contracted, but funded by the public hand, and we do this in many different domains. And so one of our concepts that we have is the so-called living lab. The living lab is basically a research lab in a certain domain. So for example, in retail, I've worked a lot there, in the last 10 years, but in the factory, for example, in the automotive domain, in power and production. So I'm also looking forward to the talk about AI and grids. I think this is also very interesting. We have a large robotics group and so on. And these spaces basically are explored together with industry. So industry is basically the main driver here. The domain kind of brings in the problems, and we then in a kind of a negotiation process we see how we can cope actually with the AI algorithms we have, and more in the last, I would say, 10 to 15 years, more and more also HCI tools and methods. It's getting more and more important, and DFKI even has now somehow an underlying claim that it's kind of focusing on human-centric AI. Again, sounds a little bit like a buzzword, but I think it nicely reflects this shift also in AI in the last 30 years, where we have more and more the consideration not only of the problem, solving hard problems, but really kind of solving hard problems together with humans, actually. And I got many inspiration. Of course, one question that you could ask, how will AI, more and more AI systems change the way we interact with those? And one, if we take the horse metaphor, one of course is that humans obviously have to give away control somehow. But they might gain a higher level of control, which is supervision. So if you think about the horse, then a very well-trained horse that is very much knows what actually the rider wants, basically, you don't have to basically do much. Yeah? If you just very subtle commands you give, a horse that is untrained needs kind of a little bit more of input and maybe a little bit more of reinforcement learning, to do, so I'm not a horse rider, so I have no idea if this is true, but in principle, you understand what I mean. Yeah. So I take inspirations actually from control rooms. I remember Wendy's early work actually, where she worked with in this kind of flight control scenario, yeah, which is exactly, that thought that these kind of control rooms already exist, so there are control rooms. In power grids, there are control rooms. Actually, power companies are very interesting because, from an HDI perspective, because they have one of the most sophisticated control rooms, even larger than the ones from NASA and so on, to control actually the grid. So very huge, large screens for researchers in visualization and so on. It's basically paradise actually to work with them. But of course, the more and more complex systems we get, the more eventually supervision will be important for humans. And supervision itself, it's a studied area, and we know that supervision comes with a large bunch of problems, So it can be sophisticating, but in terms of executing control, but it can be also very boring, and kind of having this kind of sweet spot is a challenge, And I think it will be also a challenge for this kind of human AI partnership, to keep this challenge. And one way, if we move from flight control to pilots, one way, of course, to basically keep you somehow in the mood, more or less, as a human, is of course to simulate. Yeah? Simulate interesting scenarios, that might not happen because the AI is clever enough to keep those away from you, but they might eventually happen, and then, of course, in a control scenario, be it a nuclear power plant, be it, I don't know, an airplane, humans need to be prepared. So I also believe that simulation will be a large part. Simulation also can help to mitigate negative long-term consequences of use with technology, eventually, because it's part of a training. I often like to consider this similar to physical, actually, kind of physical workouts or so, where you physically train. You simulate, in a way, kind of real work, and at the same time, kind of counterbalance actually negative effects of purely cognitive work. So, in terms of autonomy, the question is, where are we? This I guess some of you have already seen this. Those are the different levels of autonomy here in driving. And although I remember this 5, 6, 7 years ago, the tech talk from the Google engineer who was their head of autonomous driving said, my goal is that my children that are now kind of 12 and 13 never have to do a driver license, in their life. This would be actually the goal of level 5, so you don't need a driver, We are very far away from this, In many complex tasks, we are very far away from this. And the reason is that it turns out, at least in my opinion, to reach actually level 5 in all aspects of life, you basically need kind of sort of general AI, You need kind of understand what's going on. You need to have full assessment of the environment. And we are so far away from that it will be very difficult for all kind of situation to reach this level of autonomy for a long time in complex tasks. So that's actually one observation. The other one, actually, when it comes to control, how will these control rooms look like? Will they look like, not everybody has kind of, the money to install large screens everywhere. So, so it will be very likely some sort of virtual reality, augmented reality additions, you know, to add these kind of information into your physical world, you know. And you can tap once you, so this is actually a picture from a virtual reality game of climbing, you know, where you not really physically climb, but you can simulate that too, yeah, but here in this kind of virtual climbing. And what's interesting here is that with virtual reality, also augmented reality, you you're able to tap into this perception action loop pretty tightly. Yeah? This is different to simulations in front of a screen. So you can manipulate much more. Of course, again, very similar to these level 5 autonomous driving. Here we are also at the beginning. You know, even the sophisticated VR systems, they have, of course, a certain degree of immersion, but it's still kind of, we're still far away. Many, actually, senses cannot be addressed probably, simulated probably. So this is something we have to do. This is a Milram continuum from, which kind of describes a little bit, and it's from mid of 90, describes actually these different poles from real environment to virtual environment, and somewhere in the middle you have this mixed reality. And there is augmented reality, for example, where you put digital elements into the real world, so as realistic as possible. But of course also the other way around, where you have augmented virtuality, where you have basically a virtual environment and you put back stuff from the real world. And then there are also all kind of other things you can do. For example, there's an interesting kind of variation of that, that's diminished reality, where you're able to manipulate actually things that you see, and you can remove stuff. Yeah? So it would be nice, you know, you enter your room, you know, and it's nice and tidy, all cleaned up, and in fact, in reality, it's a mess, you know, and your kind of augmented reality goggles tells you all is great, you know. It's maybe not that thing that you want, but if you think about it, and if you think about what Wendy talked earlier this morning, you know, there is very strong potential for manipulation there also, you know, and also very long-term effects also on what it does to ourselves interacting with these systems. Our brain is pretty good. It's super. It has a very high plasticity. It basically can react and adapt to everything. And it's a little bit the question, you know, how we want this to evolve. Okay. So this, for example, is a VR environment where we use actually haptic feedback. Actually, this is a treadmill. Climbing treadmill. So basically you can climb, you're climbing more or less on the spot, yeah? But in the virtual realm, of course, you're climbing, you can climb in principle infinitely long, yeah, of course, since only in theory. But what you can do is you can, this is the interesting part, you can manipulate actually what you're seeing according to, since you have full control over this, you can basically change, here the holes are exactly the same, but you can change this, you know, you can basically change certain parts of the environment and just take into account what the physical world basically is providing you, and within certain bounds you can basically change actually the haptics and so on. Another, I think, important observation is that computing technology moves towards the human body. So it started somewhere in the deep cellars of mainframe computing, and then it moved on the desktop, in our pockets, actually on our bodies, on our skin. And eventually, you know, maybe in Western Europe a little bit later than in the rest of the world, it will also move into your body. Yeah? I'm pretty convinced about this. Yeah? It already did a little bit. If you think about cochlear implants or so, yeah, which are kind of defibrillators that basically kind of monitor your heart and then kind of do their own thing, you know, and you have to trust the algorithm to do the right thing. And those are, of course, medical conditions, but, you know, every kind of medical condition, if you think about enhancements, this might happen. And the question is, how does this change the way how we design interaction with the computer, you know, when it's getting more and more implicit, this respect? What are actually the role then of explicit interaction, which from an HCI perspective, I think is the interesting part, because it kind of provides that expressivity and control, you know, if you can explicitly do something. This is one example, I can quickly show you, of our own work. This is actually a trainer, a running trainer that helps you to improve your running style, so to speak. And what it does, it helps you to learn a foot running style. So not a heel running style where every step is basically you're landing on your heels. It kind of tries to teach you how to land actually on your forefoot, which some would argue, you know, is a little bit better type of running. And what it does, it basically measures your foot, your cycle of your running, each step the foot does. And then in the right moment, basically, it activates your calf muscles. And this then leads to basically your foot falling down automatically, you know, without you even kind of thinking about it. And then you land automatically on your foot, on your forefoot. And what's very interesting is this kind of system is that A, it works, yeah. B, you don't have to tell the user what the system is doing. They just wear it, and it's basically pushing them into this foot running style. And C, the learning curve is very steep. So actually, your cognitive system, although you're not consciously knowing what's going on, basically your whole system is basically adapting to it. What's interesting is we're just using it here on one calf, and it automatically translates actually to the other leg. You know, this is because this is something your brain does. You know, when there's some of uneven motion, it basically tries to compensate automatically. It's very interesting if you think about this. You know, these very implicit systems that intervene without you consciously doing something with your body. And of course, this is not high-end AI, but of course there's a little bit of a machine learning integrated and also a little bit of personalization component so that it works actually with every user. Another interesting example is actually to use EEG. You know, EEG, so brain-computer interfaces, you've heard this, you know, Elon Musk is kind of putting money into all kind of things. You know, again, here we are very at the beginning, but certain things work well, actually. And one thing is to detect, actually, what's called the error-related potentials. So whenever something happens to you that is unexpected, you know, then this kind of is something that we can detect pretty well with these typical EEG cuffs. You know? So there is a typical spike in one of the bandwidths, you know, and this is work that my colleague Elsa Kirchner at DFKI in Bremen did. And their goal there was to teach robots to do something, you know, by showing them, you know, by telling them, so through different modalities. And now the goal of the EEG here is to identify early on if the robot does something wrong, and then providing that feedback without even telling the robot, and with instantaneous, actually, in an instantaneous manner, the robot then understands immediately that actually the action it performed was wrong, you know, not the intended one from the user, and it then switches to the next possible hypothesis, you know. So it's kind of speeding up, in a way, the learning. This is actually similar to how also humans sometimes, if they can read actually the other person well, understand immediately, oh, no, this was not good, yeah, so I'm doing something else, yeah. And this is something we can tap into also as an additional signal in this respect. So so what I'm interested in is to bring these two things together. On the one hand, actually, these transfer of control, the mix of control between human and autonomous systems or intelligent systems, and then also use the virtuality continuum as basically the main interface metaphor. And here's actually a slide that I've also shown when I was in Namur, and Michelle and Wendy were present. And you see, I've changed, I switched it top down. Yeah. So this is something that I adopted from Eric Horowitz. This is from 2015, the award keynote that he gave, and he basically he discusses this relationship between human intellect and machine intellect and how those can benefit from each other. And of course, there is this kind of, sometimes I say, a little bit romantic vision, you know, that human intelligence and machine intelligence always complement each other in a way that is beneficial, because actually the outcome is much stronger than the single ones. And while this is certainly true for certain areas, it's very interesting to explore those areas, and I'm into this too. You know, this is something I find very interesting. I guess sometimes, you know, machines are just better, you know, and in other times humans are also just better. And understanding this, this kind of these different categories, I think from a research perspective is interesting, because this then leads to different ways, for example, how you would make a deployment of such a system, and we will hear maybe in the next talk something about this. I'm very curious about this. But again, you know, the interesting part here is that here we are moving into higher level cognitive abilities like planning, like developing concepts and so on, you know, which I also find interesting. So at DFKI, we have a long ongoing initiative on transfer of control. So the idea is that you have an autonomous system. The autonomous system does something, like an airplane flying you over the Atlantic, and then something happens, and the system is a little bit out of its bounds. Yeah? And then a human has to take over. And how to design actually this transfer, you know. Again, this then is, I think, an interesting HCI problem. Yeah? But it has to be tackled in a different way than the problem, you know, that a computer system makes a suggestion, then I take the mouse and then I do something, provide some input and so on. So this is different. It has a lot to do with situation awareness and so on. And it's definitely something that we will see in autonomous driving. Here's, this is something we study, you know, where we usually have these kind of secondary tasks, so people, this is in an autonomous, and then something happens, you know, and users have to take over. You know? And the question is, how do you take over, and what are the modalities that you use? Again, this research in simulation and virtual reality helps actually to understand and to investigate the right modality combination and choices, in my opinion. In driving, it's maybe rather simplistic, because the environment is much more or less under control, and we have lots of sensors already in modern cars. So this is something that can be easily done. But if you think about a household robot that helps you to clean up your room, your apartment, that would be great. Yeah, but they don't exist. Just to complicate it, you need more of general AI here, of course. But in such a case, you know, it would be great if you could teach the robot, for example, how to do certain things, what you like, what you don't like, and so on. So in fact, if you look at the transfer of control problem, then you have on the upper left, you have this autonomous system. On the upper right, you have the human or agent. And then you have these two different paths, you know, where transfer can be moved from the autonomous system to the human, usually in cases where something went wrong or something is not basically going according to plan, you know. And then you have a certain set of challenges that you see in the upper right. You need to provide explanations, not about the model, I believe, but about maybe the urgency of the situation, you know, so that users can prioritize, for example, and about the situation itself. I think this is very important. And then, of course, it can also go the other way around, you know. So you have a return of control, where humans then hand back control. And this also touches all kind of scenarios like teaching. Yeah, this is again something. So we have one scenario where a human is doing something, and you have robots that can quickly learn and jump in for humans, you know, in certain situations. You know? And the idea here is that there are many tasks, actually complex tasks, that consist of multiple steps in the production process, where humans are still much faster than robots, because of the complexity of the variation of the task. The robots could do this, but much slower usually. Yeah, and there it's interesting actually to have robots only to jump in when time is not so much of an issue, because a human has something else to do somewhere else, for example. Yeah? This is the example of the vacuum cleaner, you know. Usually a vacuum cleaner, you know, a vacuum robot that kind of roams around your house, it's usually slower than you are. You don't care because you have other things to do, you know? So time is there not so much of an issue often with robotic components. It's more about the right point in time, you know. And then, of course, you know, this is work with Hitachi. You can, once you have a tighter integration of human physiology and also the environment, you can measure all kinds of things. So for example, torque, the real, not only the applied torque on the screw, but also the forces that actually humans apply. And you can use this actually to provide more control over certain tasks. Here's another example. This is actually from work together with Airbus and Brötje. This is assembly task of a raceway. The raceway, so this is an Airbus actually in the planes, you know. They have these overhead, I think this should work. They have these overhead rails here that are at the ceiling of the cabins, more or less. And you need to install components there. This is pretty tedious actually for humans because it's overhead work, you know, you have to hold it, you have to screw it, and so on. It also includes certain chemicals that are not very healthy, so you have to wear a mask, which is pretty annoying when you apply them, and so on. And here actually there is a compound of robots working together with a human actually on this task. And just so there's one part of robots that basically change the work environment. Yeah? They move tools around, you know, and both for workers and for robots. In this case, it kind of moves tools around for other robots. You know, you have these two robotic arms that you will see, and those two robotics arms now work together actually to prepare the workpiece. Yeah? Again, you know, this is an interesting question, but this now, until now, there is no human. So you could do this differently. So this is actually this chemical solvent. Obviously, this is a fair, so we're not using it. And what you see now is a typical thing that robots have to do when the task is not super canonical. They need to calibrate somehow. This is still something that robots need to do for a little bit more complex tasks, so that they exactly know how to grasp the thing, and so that they know where it is and where it's applied. So now, since this is a fine motoric task, and there are lots of variations, you know, human would do this. And, but without actually having to hold this thing in place, you know, which is tedious, but just basically putting in the screws and tightening them, and then basically controlling the result. Yeah. So yeah, so what's this is a little bit a toy example, you know. I think it's not necessary, you know, of course, but in principle, you know, robots could also hand over tools to humans, you know, you still see, this was in 2019, it's a little bit better now, but still, so handing a tool from a robot to a human is super complicated, you know, it takes a long time. There are not very sophisticated systems out there that could do this for, in a way that humans could do it, you know. Again, you know, such a simple thing, you know, handing over a tool, you know, quickly, even under time pressure, is something that humans can easily do. They learn it very easily. For machines, it's super hard. You know? Once you have such systems, it's getting, of course, interesting because you have kind of flexible, intelligent environment. And this is now an upcoming project where we try to recognize errors and wrong actions. This is the only task, you know. And the environment basically does two things. It basically tries to prevent and correct those errors. At the same time, also teach actually the humans to basically prevent doing the errors the next time again. You know, so it's kind of a little bit like a safety net. Yeah? This is again, I think, an interesting version of a companion. You know, in a way that I could see that humans, or it's an interesting observation, how you design those systems that humans wouldn't feel patronized, but accept it as a safety net, as something very useful, to support actually their work. And the line is very thin here to design those things, and I think it requires good ideas, and also a good kind of methodological plan, how to design these systems that they are perceived actually as real companions and not as somebody who... Another example here, of course, in these systems, often you have certain elements of gamification, where you use kind of game elements in a purposeful situation, so not only out of the fun of it. But these gamification systems, again, I think a good example of systems, if they are designed wrongly, they lead actually to a negative effect, in the work, in the companionship relationship, so to speak. But if designed correctly, they can basically lead to empowerment, also more, a better actually work experience and so on. Okay, so this is actually the part about the intelligent environments and the way how we look at these transfer of control problems. Let me now speak a little bit about this virtuality continuum and how what I believe is also necessary for the simulating, for the training, is that we need to have the environments adapt actually to the users, to our 50,000 years gene program, more or less. Yeah? And one of the visions, I think it's still true, is that we still have to adapt a lot to computerized environments, There is a certain, I would say, there has been an improvement in the last 15 to 20 years in terms of how systems adapt to us. But what we've seen, and Wendy talked about this, we've seen also that adaptation, if it's done in the wrong way, can lead to a certain problematic relationship on the long term. Yeah? So again, it's important that we understand how we can address, for example, all the senses, all the human senses, and I will talk now a little bit about haptics, because this is one of the underdeveloped senses, but they're heavily needed actually if you think about augmented reality and virtual reality environments. And there is an interesting, I'm not going too much, this is from André Zenner, I don't want to talk too much about actually the areas of research that you can do. What I will talk about is haptic adaptation in real time, actually, with physical props and physical controls. Yeah, this is what I want to do. What we've done here in this research is actually we use purely passive haptics. So passive haptics is if you're not actuating the haptics, for example, through vibrotactile feedback, through something that pushes back, like a phantom device. Some of you might be familiar with that. Those are devices that are robotic components that basically simulate haptic experiences by actuating forces. We're just looking at passive haptics. So using, for example, a controller of a certain shape, and then showing in the virtual environment a different shape that is similar, actually, is a typical use of these passive haptics. What you can do is you can change the haptic properties in real time without actuating actually active feedback, but for example, by changing the shape or by changing the weight distribution. This is what we call dynamic passive haptics. And I will show you one example of such a change of passive properties that one could use. And this is the Dragon, which is actually a controller that changes actually the air resistance while interacting with it. Yeah. And how does this look like? This looks like this. So it basically is a fan that can change its opening, controlled by actually the effects that you need. Yeah. So if it's fully open, of course, there is a lot of drag in the interaction. And if you close it, there is no air resistance at all. And you can do this also asymmetrically. So you can manipulate different can produce different types of torque on the wrist and on the arm. And of course, in the virtual reality scene, you see completely different things. You know, of course, you're not seeing this fan. You see kind of a racket, for example, or a wrench or whatever, you know. And it provides a much more realistic haptic experience that cannot be or very hardly be generated by active feedback, you know. So the physical world is still very rich in terms of what how we can interact and what we can do, and the dynamic passive feedback basically taps into this. Another trend is actually control ratio, yeah. So this is something we know, display control ratio. This we know from the mouse, you know. Of course, you know, if you move your mouse an inch on the desktop, it doesn't mean that it moves an inch actually on the screen. You can basically control this. And there are tons of research in HCI on how to do this and so on and so forth. In virtual reality, the interesting thing is that you can do this unnoticed to a certain extent, because the user is basically encaptured in virtual reality. You can reproduce virtual hands, and you can do what is called in VR research target redirection. So that means when you see your hand moving in VR, you know, you can control, of course, you can, if you track the hand, you can control actually the movement of the virtual hand. So it basically, the virtual hand can do something else. You know? So it can deviate from the original path. And this is how you can control the ratio, yeah, the movement ratio. And this opens up an interesting design space, because it would allow you to do with the same physical device, the same physical proxy, for example, a slider here, yeah, you can basically mimic in virtual reality with the same movement different scaled movements. So you could have different sizes of sliders, yeah, in the virtual reality that is operated by one physical slider. Yeah. So, and the question then, of course, is one-to-one is clear. But what about smaller movements? What about larger movements? Where are the boundaries that are? And there are actually two boundaries that are interesting from a cognitive point of view. One is actually the boundaries that you don't notice. So what is? And I tell you, I don't have the figures here, but it's roughly about 10%. So 10% of a scale you can get away with. But then there's a much larger, actually, other boundary that is noticed but is acceptable. Yeah. And this is, again, interesting, because from an HCI perspective, then this is becoming part of a tool, yeah, of an extension that you have, you know, that is kind of not annoying you, but empowering you to reach further away in the virtual space to interact with objects, for example. Yeah. And of course, you know, it's in principle you could use one slider, yeah, one physical slider, or a few physical sliders to interact with many different variations of physical sliders. And if you use hand redirection, you could even get away with one. And when you see, for example, the virtual representation. And there's no hand representation here, but of course you can put a hand representation, and then when you move your hand to operate a different slider, if you do a redirection always to the same physical slider, you know, you can get away actually with one slider to operate a whole range actually of physical ones. And yeah, so this is, I think, again, you know, for interaction and for simulation, those are prerequisites that you need to understand and that you then can use actually to bring the simulation part together actually with the intelligent environments. And then there's also a large the question how to design actually haptics. So and again, how to design interaction. Wendy talked a little bit about this. I think this is also still for researchers an interesting question when it comes to these companion partnerships. It's also an interesting question when it comes to haptic feedback, actually, in virtual environments. And here, this is a small idea, and I would like to close my talk with that idea. It's about in situ prototyping of vibrotactile feedback. So this is, again, classical vibrotactile feedbacks that you know from your watch, for example, or from your phone. And the way how the idea works is that you use your voice, actually, to design it. Because so far, when you look at vibrotactile design, this is all about controlling the motor and so on, you know, so the different input levels and so on. You have patterns that you use, you have little design programs that you can use with all kind of parameters, amplitude, you know, and periodicity and so on. And here is, we get all rid of that and we just use our voice, because our voice has many aspects that can be used actually for vibrotactile design. And the video shows a little bit how the idea. Hoppala, it should start. Let's see if I can start it. Yeah. I don't know, you might not hear it, so I'm trying to mimic what they're doing. Yeah. So again, you know, let's assume you have kind of a button and you want to provide a vibrotactile feedback to that button. And usually the idea is, usually what designers do, they have this kind of tool, then they have design space, they choose a certain point in experience, then they put on the VR glasses, they test it, and then they go back. And this can be all done actually in VR. The whole design can be done in VR. Here, for example, the lightsaber, which is of course only a controller in reality, and now when she does the movement, she can record the vibrotactile feedback by vocalizing. So she does for example, or or so. Yeah? And the AI system actually, the small machine learning component, translates this actually into, in fact, it's a very simple signal processing algorithm, translates this into vibrotactile feedback. And this then can be altered and modified in VR. So you get actually a console in VR where you can modify this and then try again, you know, and add to this and so on, you know. And you get these spatial temporal mappings. And again, you know, from a design perspective, it's interesting to do this all in one space. So you don't have to put off your glasses, you know, you keep them on, and you use all the modalities that are available to you. And I was really astonished, you know, when we originally discussed this idea. I was not so convinced about it. I thought it's you know, it's a toy application, but in fact it works pretty well, and the vibrations that it produces are very convincing. Okay, let me please conclude. I talked about handovers, and why I believe in these kind of surveillance scenarios they will be important. Yeah? There is, of course, still a little bit the question, how will this look like? In terms of a car, you know, as I mentioned, this is pretty clear, well-defined intelligent environment in a way. But what about another scenario that goes more into, for example, control of the fleet of drones that does all this future delivery of packages and so on, you know? How does this, or even, this is also this robocars, you know, where very likely when they're coming, they will come, you know, for certain areas of a city, very likely where human drivers are not allowed anymore or so, yeah, or on special lanes. But then still, there will be a human operator basically controlling this fleet, you know. And controlling a fleet is again another problem than just being kind of taking over from one intelligent system. So those are interesting questions, yeah. And again, you know, what's the role of simulation here? And then the other part is how to design the simulation environments, yeah, that I also believe will be necessary, you know, and will be one of the prime maybe in 10, 15 years, one of the main actually control rooms will not be physical but virtual. And with that, thank you very much. Looking forward to the discussion.